When I was a kid, my dream was to become a doctor. Then I discovered my passion for maths and physics in high school. And when I first heard about medical physics, I thought it was the perfect combination of my interests. Hi, my name is Allison, and this summer I had the opportunity to complete a physics vacation scholarship at Sir Charles Gardner Hospital under the supervision of Professor Martin Ebert. My project is deriving an analytical solution for optimizing tumor control probability given a probabilistic clinical target volume for prostate cancer. And why is this a significant area of research? Well, prostate cancer was the most commonly diagnosed cancer in 2018, with 21,853 new cases in Australia. Nearly two-thirds of all cancer patients are treated with radiotherapy, which is used in isolation or in conjunction with radiotherapy and surgery. Traditional treatment plans for prostate cancer involve irradiating the prostate with a high, uniform dose of radiation using external beam radiotherapy. However, this does not account for prostate cancer's significant spatial, genetic, and morphological heterogeneity. An alternative approach known as focused therapy redistributes the dose to be more concentrated in cancerous regions and statistically high-risk regions while minimizing the dose administered to the healthy tissue. Radiotherapy treatment planning is complex and involves the definition of different volumes. The MRI image of the patient shows the macroscopic tumor volume known as the gross target volume or GTV. A physician would determine the clinical target volume or CTV, which extends the GTV to account for the microscopic extensions of the tumor. The planning target volume, or PTV, is the volume to be irradiated and encloses the CTV. There is inherent uncertainty in determining the PTV, as it must account for the motion of the prostate and uncertainties in imaging. In the case of prostate cancer, the CTV is the entire prostate and the seminal vesicles. The tumor control probability, or TCP, is the probability that a given dose of radiation will eradicate all the tumor cells. The key problem in radiotherapy treatment planning is finding a dose distribution that optimizes the TCP but minimizes the dose administered to the surrounding organs at risk. This is crucial to reduce the negative side effects associated with prostate radiotherapy, including urinary problems, abdominal cramps, and bleeding. Traditional CTVs are binary in the sense that a prescribed dose is administered to the target volume and a steep decrease in dose is administered outside the CTV. A significant amount of research has been dedicated to finding an accurate CTV. Ankelbach et al. Developed computational methods to determine the CTV. The three primary goals were automation, consistency, and improvement. The guidelines used to define the CTV were implemented by a computational algorithm to automate the process. However, the binary nature of the CTV studied by Ankelbach et al. Fails to account for the significant motion of the prostate and a continuous fall-off in tumor density. Shusharina et al. Addressed the continuous fall-off in tumor density by introducing a probabilistic alternative to the CTV. This model was used to numerically optimize the TCP in the glioblastoma. Bortfeld et al. Extended Shusharina et al.'s TCP op optimization on a probabilistic CTV to consider a non-convex subjective function, which more accurately reflects the nature of the TCP. Shusharina et al.'s convex objective function is inaccurate for prostate cancer due to the low alpha-beta ratio compared to other tumors. However, neither researcher obtained an analytical solution for the optimum dose distribution. In both papers, the voxels were assumed to be independent as it is computationally expensive to perform the optimization on dependent voxels. In this project, I extended the probabilistic CTV introduced by Shusharina et al. To provide analytical solutions for an optimal TCP. With an analytical method of optimizing the TCP, it is anticipated that the TCP model can be extended to include some of the constraints which make a numerical solution computationally intractable. In addition, an analytical solution is more versatile and not limited to prostate cancer. As a first step to an analytical solution, we will consider a constant alpha-beta ratio over all voxels, which are assumed to be independent. The following formula was derived given the linear quadratic relationship and the Poisson distribution. Random sampling was used to obtain the tumor probability, radiosensitivity, and cell density. To account for the errors in determining these values, here gamma, epsilon, and kappa are normalized probability weights that add to 1, and GI, LI, and K are the number of samples obtained. PRG and ρRL represent the tumor probability and the cell density obtained in each sample for the particular voxel respectively. VI and DI represent the volume and dose of each voxel respectively. N is the number of radiotherapy treatment fractions, and Tx and Tpot are the expected treatment time and potential doubling time of the cancer cells respectively. This relationship was further simplified to give formulas where alpha was constant and the quadratic term was ignored. In addition, instead of using sampling to obtain the various values of P and ρ, the mean value of the tumor probability and cell density were used. McNeil introduced the zonal anatomy of the prostate, where the prostate was divided into the anterior fibromuscular stroma, shown in green, and 3 zones that contain glandular tissue: the transition zone, or TZ in blue, the peripheral zone, PZ in orange, and the central zone, CZ in yellow. It has been observed that 68% of cancer tumors are found in the PZ, 24% in the TZ, and 8% in the CZ. Men with carcinomas located in the TZ have higher biochemical recurrence-free survival rates compared to carcinomas located in the CZ and PZ. The TCP formula was optimized given a fixed total dose. Ebert and Holbert's method of optimizing the TCP using Lagrange multipliers was used to optimize the TCP formula shown earlier. We obtained the following results for our analytical optimization. The validity of the analytical optimization was tested against a numerical optimization, which determined the optimal dose distribution of a sample prostate. The sample prostate was generated using data from 63 patients in the dataset used by Finnegan et al. To generate their statistical voxelized model of prostate cancer. The cell densities were calculated using the computational method introduced by Benoit et al. MRI imaging was used to obtain the contouring of the prostate, which was used to calculate the tumor probability in each voxel. The patient's cell density and tumor probabilities were fitted to a log normal and normal distribution respectively. This sample prostate data with tumor probability and the cell density of each voxel was visualized as a heat map using the Python module matplotlib. When my model was tested against this data, I obtained complex solutions for the dose in each voxel. This is a non-physical solution and indicates that there was likely a calculation error when deriving my model. This could be amended by checking the values of V and B to ensure that they give a real value for the dose, and possibly making adjustments to account for negative values which give complex solutions. A possible direction for future research is to investigate analytical solutions for the more complex TCP models introduced in my talk. In addition, an extension of this solution to account for the organs at risk and minimizes the dose administered to them could be developed. Throughout this internship, I have not only received a taster of research in medical physics, but also developed my literature review and scientific communication skills. I would like to thank Professor Martin Ebert again for this valuable opportunity. It confirmed that medical physics is the perfect career where I can combine my interest in medicine, mathematics, and physics. Thank you.
All right, thanks, Allison. Thanks for that. Does anyone have any questions for Allison?
That's perfect. Thanks, Allison.
Yeah, it was amazing. Look, I really congratulate you. You really picked up things very quickly in a short amount. You only had a short amount of time to get your teeth into this work, but you clearly understood it very quickly and very well. So I think there's a lot of scope there for you to take what you've done so far and expand on it more. I'll just stop recording unless there are any other questions. Right, stop recording.